I'm going to start by using the tool that allows you to automatically go through a wizard and set up a project. I'm going to call this example watershed, and it doesn't actually create a WMS file until you click save. Next, my project boundary, you can zoom in on whatever area in the US you are interested in having. This is the location where the watershed I'm interested in, and you'll notice that as soon as you do that, sometimes the tool pops behind when WMS, and so you need to click that a few times to bring it back up. It fills in the boundary for the project. The next thing is that you tell it to use the web services, connect online to get some of the data, and the data I'm going to ask it to retrieve is 10 meter resolution elevation data. And I choose 10 meter resolution data because this is a relatively small watershed, I already know in the back of my mind. I'm going to get this land cover database, which defines the land uses in the area, but I'm not going to include the soil type because that's been failing for me recently, and I already have the soil type data downloaded separately from the NRCS. I click on this and it automatically downloads the data and asks for a cell size. That's a suggestion of how closely spaced I want each pixel to be on the data. The land use data, its origin is 30 meter spacing, so I'll just pick that as the default. And if I close this, you'll notice over here now I have the DEM file that's been read in, and if I click this grid on, it's the land use data. Those different colors correspond to different types of land use, like urban areas and forested areas and so on. So I'll turn that off for now. The first thing I want to do is go into the drainage module and have it calculate topaz. This is a process where it is looking at each of the pixels and asking itself where would the water flow to if there's a rain event, what direction does the water move, and it's trying to find places where there's a really high accumulation of upstream cells feeding to it, and that's where it thinks there's going to be a stream. So I'll just say OK. It starts its calculation. It's comparing all these adjacent cells. The program terminates. We could close. And then what it does is it identifies with blue where it suspects streams will be. And I can adjust how dense those drainage cells are by changing the minimum accumulation for display. For example, if I want, anytime there's more than a half mile, 0.5 upstream, then you see that there's more of these that are shown now, or I can even go to 0.1, or really whatever you choose, and it will start to assume that there's a stream there based on how much watershed area is upstream of it. I know that where I'd like to put my watershed outlet is around here somewhere, but just to help me find a little bit more precisely, I will get online maps, and the World Street Map I feel does a pretty good job, and it takes a while for it to stream that data. It's going to be reading that. You see here it says processing. I think what it's doing is it's getting that from a server. It's sort of streaming that image, and the first thing that I usually do is I will right click and well, maybe the function's changed a bit, so I'll just pick where the crossing location is, put an outlet where the stream goes under the road, and you notice on the map it says the stream's going to be here, but WMS, or Topaz rather, guessed that the stream would be here based on what the DEM is. That's fine. It doesn't really matter it being off a little bit, and that's probably 10 or 20 meters at most. It's still going to do a really accurate job of calculating the watershed area, which is the next thing I want to have it do. I'll click Delineate Basins Wizard, Delineate Watershed, and now what it's taking a look at is looking for the ridge lines and where are all the places that are going to flow at that outlet that I've just selected. The next thing I can do is trim the DEM to throw away any of the elevation data that I'm not going to end up needing. And you notice that this is saying processing again, because what it's doing is it's once again streaming that, and it can be a little bit slow. Usually what I'll do is I'll export the image to a static map, and so that I don't have to wait for it every time. And so I'll just say World Street Map, that's fine, and it'll download that. Once it's exported it, then I can turn off the streaming version because I'll have a cached local copy of that image. While it's downloading that, I'm going to go through the, no, it won't let me do other things while it's downloading. So I'll wait and pause this recording as it's downloading. Okay, so now I have a local copy of that that's cached, and I'm going to delete the image that's been streaming to me. And so now you'll notice that when I zoom in, I don't have to wait for it to process and so forth. It wasn't so bad before, but now it's not a consideration at all. So what I was going to do is trim out the DEM data that's not applicable. Right-click, trim, polygon, which allows me to interactively select the area that I would like to keep the DEM data. I still need it because it's going to be calculating slopes and all sorts of information when I calculate time of concentration. So I want to have the DEM data behind the watershed area. Alright, so I've got the trimmed data here and the original data. I suppose I will throw away the original data since all I want to keep is the trimmed data. Okay, save it and turn that off. I don't necessarily have to see the DEM. What I've got right now is the elevation data that's been trimmed, and in the background there is the land use. What I'll do next is add, right-click, shapefile. This is soil data that's come from the Soil Data Mart, and this is Kanawha County in West Virginia. The shapefile that I add is the big one with all the data there. And the first thing I'm going to do once it adds is right-click on it, join NRCS data. It goes into the data tables and joins the hydrologic soil group, and that's not automatically included in the shapefile, and so it has to join some information from a data table that's held separately. So I'll click OK and it joins that. The option was there, by the way, that if I wanted to ensure any missing values, if there was any area that didn't have a hydrologic soil group, gives you the option of assigning it a hydrologic soil group. And it's picking D, I think, because it senses that that's the most common hydrologic soil group. However, in my experience, I haven't actually found any polygons that didn't already have a hydrologic soil group assigned, and so I usually don't bother doing that. Okay, so this is now the soil group here. I want to create a coverage that is a soil type coverage, and I'm going to put the soil that's now in the GIS data up into a soil type coverage. And you can calculate curve number directly from GIS data, but for very large watersheds where you're having to combine multiple counties of data together, sometimes it can be overwhelming, just too much data, and so I generally will clip out the section of the data that I need. These toolbars are in a weird place. Okay, so I'm going to select those polygons that are inside of my basin, and you notice that it selects any outside that were partially in it. And now that I have joined the data and selected the polygons that I want mapped into my new soil type coverage, I'm going to say mapping and take the existing GIS data, put it into a soil type coverage, and what I'm really interested in is that it makes sure that the hydrologic soil group is defined and that it's going to see that as an SCS soil type. So I say next, and it copies the relevant polygons from the GIS data into the soil type coverage. And so if I turn off the GIS data, you can see that now these polygons here are in the soil type coverage. I don't have to necessarily have them displayed for them to be usable when I calculate curve number. And just to summarize right now, what I have is a watershed boundary with DEM data. There's land use data, and here is soil type data. And that will enable me to go into the hydrologic modeling module, and if I was setting up a HEC-1 model, for example, I can have it calculate these GIS attributes. That means it's going to calculate the curve number using the soil type coverage, the grid, which is the land use grid for determining land use, and I want to import a table that will define what combination of land use and soil group corresponds to what curve number for when it's going to be calculating a weighted curve number for the watershed. And so you can see now here's a classifications. If you've got evergreen forest and land type, soil type A, then that would be a curve number of 30, 55 for soil type B, and so on. It's got all these different land use classifications, and then their corresponding 4 soil type groups. And when I click OK, it's going to calculate a weighted curve number for the basin. You can see 65.3 when it looks at all of the different overlaying land uses and soil types. And it is displayed that, I'll move the label out of the way if I can. There's the curve number that it's calculated. Of course, if I want to delineate the watershed a little bit differently, if I wanted to say, let's also split the watershed in half by putting an outlet there, I can have it delineate the basins another time, and it splits the watershed based on where I put that other outlet. I can go through this process again of having it automatically calculate a new curve number for both of those sub-basins, which it's done. You can see it's calculated a new curve number, and so now it updates the curve number for both of those, you can see. Now, if I want to actually execute the model, then I can go into job control, and one thing I'll usually do is increase the number of hydrograph ordnance from 100. I leave it at 15-minute spacing, but I'm going to want to make sure that I capture the entire event, so I'll say, just to begin, 150 hydrograph ordnance, which means there's going to be 150 15-minute time periods. I'm going to want to enter in some of the information for each of these watersheds, and so, for example, precipitation, let's just say, for example, that inside of this basin was a 3-inch storm, and now the temporal distribution of it is a type 2 storm based on the part of the country that I'm in, and so now this says how much of that 3 inches of rain is going to be during a certain 24-hour storm time period. Okay, so the precipitation has been defined. Loss method, it's going to use the curve numbers that have just automatically been calculated. For the unit hydrograph, I'd like for it to calculate the lag time based on the basin data, and if we look at the lag time based on the SCS method, it includes the watershed length, curve number, and the slope, all of which has been defined by the DEM data or the curve number data that's based on GIS data that's been downloaded from online. And so it calculates the approximately 0.7 hour lag time for this particular sub-basin, and I can click from the sub-basin I'm selecting right now, sub-basin 3B. If I click to this, now the routing data, it's looking at the reach between sub-basin 4B and the outlet, and so what that would enable me to do is define some information about the channel there. If I wanted to say, for example, let's go to, maybe I was on the wrong stream. Yeah, okay, this is now looking at a stream reach. It knows the length of the stream, the slope of the stream based on GIS. Now I'm going to have to approximate the Manning's N value. Maybe this is a relatively smooth stream. I'll just give it some N value, estimate it's a trapezoidal channel that's 15 feet wide, and the side slopes on it are 2.5 to 1. And so what that's going to do is provide a channel geometry that it can route the flow through. Okay, so now I'm looking at basin 3B. You can see here that's the one I've already defined the information for. It knows there's a 3-inch storm here, and it's looking at the temporal distribution of the storm. It knows the area, basin area is there. Okay, so let me go over to the other storm. I'm sorry, the other basin. I'm going to also likewise say that there's 3 inches that falls into this subbasin, type 2, 24-hour storm. I could select both of the basins at the same time and define the precipitation for them both simultaneously, but I'm not going to, because I like to double check each of the basins to make sure that everything's calculated the way I want it to be. And it automatically gets the watershed length, curve number, slope for that particular subbasin. Okay, so now all these parameters are defined, and I can have it run the simulation. And it asks, where do you want to save the data files? And it likes to be pretty close to the root. It doesn't like to be buried in a bunch of subfolders, and so I'll just say, we're doing it here in this YouTube test thing here, HEC-1. Alright. And have it run. It automatically runs, stops, and then reads in the hydrographs, and I can look at a hydrograph for a particular subbasin. This is for that western watershed, and it says the peak flow rate there is 174 cubic feet per second, and it has a hydrograph for the entire event. This one's pretty flashy because of how steep it is. And we have the other subbasin, in this case 191 CFS, and it has the combined hydrograph, including routing of the upstream watershed through the channel to the outlet, combining the 2 outlets together. Here's my hydrograph. If I wanted to have an Excel data file of this, I can right-click and say export/print, and I don't want to export an image of it. What I would like to have is a file, and I'm going to browse to where the file is. This could maybe be, well, it's not an image that I want. I want the text or data. So I'll browse to the file location and call it hydrograph data.txt. And it's going to give me the option, what kind of data do you want? I'll take the data and labels, and what I want to have is actually the table rather than a list, and I'll have the rows. Each row will be the points, and if there were multiple, each column would be subsets, meaning if there were going to be multiple basins, or if there are going to be multiple simulations all together in one. So I'll do export, and it creates a file that I can go and open. This one. I'll open up Excel. Well, we can look at it in the text file, and you can see it's just time and flow rate data. But I can open up Excel, and open that same file that we were just in. Have it show all different file types. Okay, and it brings open the text import wizard, and I want it to notice that it can be a comma that defines a spacing as well. Finish, and then here this is time in minutes, and this is Q in CFS. Alright, and then with this, if I wanted, I can create my own hydrograph. And there it is. So that's essentially how you start from scratch and get the data from online. One interesting feature that I rather like is I'll delete these existing hydrographs here. Delete them. One sort of value-added thing is if you need to do a lot of simulations at the same time, then we'll go into the rain gauges, precipitation. I'm going to define -1 as the depth. I'm going to do that for the other one as well, and that's a special indicator I can give it that I want it to get the precipitation depth somewhere else. And that somewhere else is that I'm going to do what's called a stochastic model. And let's say I want to have 5 different models. And I'll define that there's going to be variation in precipitation, and -1 is the trigger that it's going to find a lot of different precipitation data. And so I can say that I want it to run models where there's 1.5, 2, 2.5, 3, 3.5 inches of rain. And it's going to run all these 5 models in a row so that I didn't have to go through and manually run it a bunch of times. So okay, it set it up, sort of made a batch. This is a batch function. Run the stochastic model, and what I would like to see, it'll show you all the hydrographs, but I'm most interested in what's happening at the point 3C, which is the main outlet for everything. So click that, and it starts saying it's doing simulation 1, 2, 3, going through all the different precipitation depths. And then when it's finished, it will show me the hydrographs for all of the different precipitation depths, so that if I export that data, I can just get the text data. I want a file. I'll browse to the location. This is going to be MultiSimulation.txt. And again, I'm saying in this case, I'll just take the data. I don't need those labels up top. It doesn't really help. I want it to be a table and points/subsets, because I don't want each time interval to be a column. I want each time interval to be a row. Export. And now if I start over here, new, and open this hydrograph data MultiSimulation, going through here, there's commas that will define the gaps between them. Finish, then this is going to be time in terms of minutes. I'll delete all these extra time columns. I don't need them. Alright, and it's a little bit strange. It goes backwards, and so my precipitation depths that I had defined, if we go back to the stochastic model, what I'd said was going to be 1.52, 2.53, and 3.5. It does the last one first. So this one is P equals 3.5 inches, 3, 2.5, 2, and 1.5 inches of rain. I think it puts the most recent one first or something. I don't know how it necessarily builds that. And the way to know for sure is you just look at the flow rates. What has the highest peak flow rate? It's this column, and that's going to be the one that has the most rain. And so this can be really useful if you have to do a lot of simulations, like if you need to find out the variation of what would different curve numbers or different precipitation depths. If you want to illustrate uncertainty, then that batch way, the stochastic model is a really nice approach. So that concludes this demonstration.